Okay, in this video we're going to look at applications of vectors. Now, those will include some of the products that we calculated with in the last set of lectures. So the scalar product, the dot product, and the cross product. So we'll look into a little bit more detail about what we can use these vectors for. But before we go into that, I'm going to do an application of vectors that is a lot like a problem in this assignment in question 9. So I'll point out the similarities as we go along. Okay, the question I want to answer is this one, which I've just made up. A boat in the ocean aims to travel to a lighthouse that is located northeast from the position of the boat. And so I've drawn a little picture here in Microsoft Paint. The boat travels at a speed of 25 kilometers per hour relative to the water. So let's assume that it can travel with respect to the water at 25 kilometers per hour, and it does so at its maximum, 25 kilometers per hour. However, the ocean current pushes the boat west with a force pushing at 10 kilometers per hour. What is the actual velocity of the boat relative to the lighthouse? Alright, so what we need to do is work out where the boat is actually going. So it might be heading off, if you just look at these two vectors, it might be heading off somewhere up and to the left, or up and perhaps this way, depending on the strength of this current relative to the 25 kilometers per hour northeast. Alright, so we need to set out some letters. So I'll say let B be the attempted velocity of the boat. Alright, and then let's let C be the velocity of the current, and then let A be the actual velocity of the boat relative to the lighthouse. Okay, and so now we have the fact that the two velocity vectors should add up. So we should have A, the actual velocity relative to the lighthouse, is equal to what the boat can do, or is attempting to do, plus what the water current does. Okay? So if we just set out these vectors, we've got to find the components of the vector B. So the vector B, now northwest, that would be 45 degrees from the horizontal, which is 45 degrees from north. Sorry, that's northeast I'm talking about, right? So northeast, what the boat's trying to do. So 45 degrees east of north, or 45 degrees north of east. So here I can set it out as the vector, the magnitude times cos of 25, or sorry, cos of 45. So the magnitude is 25. So 25 cos of 45 degrees, and then the component up will be 25 sine of 45 degrees. And then the vector C is minus 10, comma 0. And so all we really have to do in this case is add the two vectors up, but we might want to simplify first. So I'll go ahead and simplify the vector b with my calculator here. And I've got to tell it that I want degrees, or I meant degrees. Okay, so we have 25 on root 2, comma 25 on root 2 for C. Or sorry, for B. Okay, now C is pretty clear. So again, we just need to add these up. So A is equal to the sum of those two. So this one plus this one. All right, well that's easy. We just have 25 on root 2 take 10, comma 25 on root 2. Okay, and now you could also calculate the magnitude of this, but it might be easier at this point to approximate this vector. So let's go ahead and approximate that. So here I'll just introduce a decimal number to make that approximation. So I get this approximation. So I'll put equals, but it's really an approximation. And then I'll chop it off somewhere, so I'll go 0.68, and here 0.68 as well. Okay, good. So we've got an approximation of the vector A. Now on top of that, we might want to calculate the norm so that we can report the speed. So the norm of this vector, I will take the square root of the sum of the squares . All right, and we get 19.273 for that. But if I'm rounding this to 2 decimal places, then that's 19.27. So I'll say the speed, which is different from the velocity. Note that this over here is the velocity. So the speed of the boat relative to the lighthouse is 19.27 kilometers per hour if everything was given in kilometers per hour. And I think it was. Okay, but note that this is a speed, not a velocity. This vector is the velocity because remember it's velocity vector. Okay, so I'll cut these little calculations. And then I think we're ready to move on. Oh, I should note. Okay, in this problem here, you're essentially given the attempted velocity of the plane, and you're given the actual velocity of the plane relative to the ground. So it's not quite the same as this, is it? Because here we had to calculate the actual velocity relative to the ground, whereas you're given the actual velocity relative to the ground. So you have to solve an equation. Okay. Let's move on and have a look at applications of vectors. So we're going to look at scalar product, dot product, and cross product, and we did cover these in the last video that I made, but we're going to go into some more detail essentially and see how we might use some of these things. All right, example 5.1. What is the angle between the vectors A equal to 3, 2, 1, and b equal to 0, 1, minus 1. So here on the right hand side of my screen, I've got the same problem, but I've actually plotted the two vectors. So in red here, I've shown the vector 3, 2, 1. And in blue, I've shown the vector 0, 1, minus 1. So this is j hat minus k hat in blue. And the red one is 3i hat plus 2j hat plus k hat, shown in red. But what's the yellow plane, you might ask? So the yellow plane there is the plane that is parallel to the two vectors that also contains the point, say 3, 2, 1, on the plane, right? Because remember, you can move these vectors around. I could shift this vector. It just must maintain its magnitude and direction. Because remember, a vector is defined by its magnitude and direction, not its position in the vector space. Okay, so I've put the positions so that I can represent these on a plane. And I've shown the plane there. Okay, so what you're doing when you're calculating the angle between two vectors, you're calculating the angle between the vectors, but here you can see what that angle should be, right? It looks like it's slightly less than 90 degrees, perhaps, right? Depending on the scale of this plot. All right, and I think after this, we're going to actually show you how to calculate the plane itself, with the understanding that the plane we're looking for contains the point 0, 1, minus 1. All right, so how are we going to calculate the angle between these two vectors? Well, we've got this formula that we learned in the previous section, that a dot b is the norm of a times the norm of b times the cosine of the angle theta between a and b. So this angle in here from a to b and from b to a. Okay, so we calculate the norms of each of those vectors. So the norm of a is the square root of 3 squared plus 2 squared plus 1 squared, which is root 14. And the norm of b is the square root of 0 squared plus 1 squared plus minus 1 squared. And that is the square root of 0 plus 1, which is the square root of 2. So in the formula, we would need to multiply together these two norms and put them there and there. Okay? Now the dot product, if we just multiply across the components and add the result, we have 3 times 0, and then we have 2 times 1, and then we have 1 times minus 1, and we add those together, so we have 0 plus 2 plus minus 1, which is 2 minus 1 is 1. So using this formula here, rearranged so that cos of theta is the object, we've got cos theta is a dot b over the norm of a times the norm of b. So we've worked out that the dot product is 1. We've worked out the two norms. So we have 1 over root 14, root 2. And now, since root 14 is root 2 times root 7, we have 1 over 2 root 7. And we can simplify that. So you can put it in the calculator and you'll get 0.189 and so on. Or you could rearrange this multiplying top and bottom of this fraction by the square root of 7. So when you do that, you get 1 over 14 root 7. And that process is called rationalizing the denominator, right? So we've got a nice little recipe for the number that is approximately 0.1890. Okay, now remember, to find the angle, we need to apply the inverse function of the cosine function. Now in your calculator, that's cos superscript minus 1 of 0.1890, but here I call it arc cos. So I take arc cos of 0.1890 and I get 1.3807 radians, but I can convert that to degrees by multiplying by 180 divided by pi, and so I get 79 degrees basically for the angle between these two vectors, and it looks approximately right. Again, depending on the scale of the way this diagram is plotted here. So it's slightly less than 90 degrees. All right, so now I'm going to add a little bit more to this question because I can see another application of the cross product that I can just introduce here. So I've got the question here that I've added. Find the plane shown in yellow if it contains the point 0, 1, minus 1. All right, so I said earlier that this plane is parallel to the two vectors A and B, the red one and the blue one. So if I want to find a vector that is perpendicular to both, I can take the cross product. Now, why would I want a vector perpendicular to both? Because when I get that vector perpendicular to both, that actually tells me the description of the plane in yellow here, and I'll show you in a moment. So first, I want to calculate the cross product. Okay, so on my computer here, I'm going to insert a 3 by 3 matrix. Okay, now it's just got ones and zeros in it, but I'll change the entries. So in the top row, I want to put ijk. In the second row, I want to put the vector A, so 3, 2, 1. And in the third row, I want to put the vector 0, 1, minus 1. Okay, and then I want to take the determinant of this because I'm calculating the cross product. So I'll write some English here. So A cross B and we use the times sign for the cross product, remember. So this is given by the determinant of this matrix. Okay, I'm going to make this a comment on my page here so that I can calculate in this window. Okay, so when you write determinant on a page, you could write out the words det and then have your matrix, or you could just change these curly brackets to straight vertical brackets, and that would suggest that you're talking about a determinant. Okay, so I'm just going to write determinant and get this software to calculate it for me. So it gives me minus 3i plus 3j plus 3k. And so I can report that A cross B is equal to the vector minus 3, 3, 3. Okay, now what I do to get the equation of the plane is I use these coordinates in a scalar equation of that plane. Now remember what I have. I have a vector that is perpendicular to both. So let's just write that. This vector is perpendicular to both A and B. And we call it a normal vector. To the equation of the plane that is parallel to both A and B. All right. So now, how do we use the coordinates there to form the equation for the plane? So it's just minus 3x plus 3y plus 3z is equal to some number on the right-hand side that we don't know yet. So I'm going to call it d. So you see what I've done? I've calculated a vector perpendicular to both A and B. I've taken the coordinates, I put them as coefficients of x, y, z, and then I put some proposed number on the right-hand side that we have to work out. Okay, but assuming that we have a point, so 0, 1, minus 1 is a point on this plane, then it satisfies the equation, right? So x equals 0, y equals 1, and z equals minus 1 satisfies the equation. So I'll copy this, paste it below, and I'll sub in the 0, the 1, and the minus 1. And you'll see that allows us to solve for d. Okay, now let's simplify this. So we've got minus 3 times 0 is 0. So d is equal to 0 plus 3 minus 3, and you get 0 for that. So we have the equation of the plane, and this is a scalar equation. It's just minus 3x plus 3y plus 3z equals 0. And I could simplify that, right? So we could say, well, we can multiply by 1/3 throughout and even rearrange this. So you would have minus x plus y plus z equals 0. And if I solve this for z, I could put this in a way that's more similar to the equation y equals mx plus c. So I could write z is equal to x minus y in another form, right? So the three of these are equations for the very same plane. It's this yellow plane up here. Okay, so in summary, if you want to find a plane that's parallel to two vectors, take the cross product of the two vectors, use the use the coordinates as coefficients of x, y, and z in the scalar description of the plane, or scalar equation of the plane. And then use a point that you know that's on the plane to find the right-hand side d. Okay? All right, well, let's move on. So the next question says, for the vectors a equal to I plus j minus 2k and b equal to 2 minus j plus k, what is a cross b? Well, again, we just take the vector a, we put it in row 2. Now notice a is on the left of the calculation, and if you were to reverse that, you'd get the minus of this result. So a goes on the left, a goes on the second row, b goes on the third row. Okay, so we evaluate this determinant, and remember the I, j, and k are placeholders, so we can say that the first component of the result is 1 minus 2, which gives minus 1. The second component is minus in bracket 1 minus minus 4, so minus 5. And then the third component is minus 1 minus 2, so minus 3. And this gives a vector that is perpendicular to both a and b, right? And so remember, you could use this to give a description of a plane that is parallel to both a and b and contains any point that you choose. All right, so a cross b is pointing out towards the bottom left of this page. Now the next part of it says verify, or to verify that a cross b is perpendicular to a, you could then compute the dot product, right, and show that the dot product of a with a cross b gives 0. Similarly, a cross b dot b gives 0. So we see then that a cross b is in fact perpendicular to both a and b. Okay, now I want you to get out your right hand if you have one. So you're pointy finger should represent on your hand the vector A, the middle finger should represent the vector B, and it tells you which way A cross B should point, right? So it should point in the direction of your thumb. Now I remember this in a slightly different way. So what I would do, let me just make sure these are the same thing. Okay, I would take my thumb, point it, have it be A, my pointy finger be B, and then the middle finger would tell me the direction of A cross B. Alright, so whatever you do, make sure it agrees with this right-hand rule. Now, is there a left-hand rule? Well, no, because the left hand would give you the opposite direction, you see. It would give you B cross A, where A is the pointing finger and B is the middle finger. Right, so that's why it's a right-hand rule rather than a left-hand rule. Okay, so the direction of the vector A cross B can quickly be determined using the right-hand rule. Yes, all right. So the cross product is not commutative in general. We've already seen this, right? You get the minus of the other vector. So in other words, T cross S is minus S cross T. All right. So let's compute the cross product between some of the standard basis unit vectors, so the I, J, and K. All right, so we have I cross J, and now you can do this with your right hand. So if, remember, I goes parallel to the x-axis, J is parallel to the y-axis, and Z is parallel to the, or K is parallel to the z-axis. So I cross J gives K, and you can compute I cross J using a determinant, right? So if I just did that here, so I cross J would be 1, 0, 0, and then in the second row we would have 0, 1, 0. Okay, you see it gives K. All right, I cross K gives minus J, J cross K gives I, J cross I gives minus K, K cross I gives J, K cross J gives minus I, and I cross I gives the 0 vector, J cross J gives the 0 vector, and K cross K gives the 0 vector. In fact, if two vectors are parallel, then their cross product will always give 0. Alrighty, so we've just done this calculation here, but the details are on the page. And I've just said this result, theorem 1. If so the vectors A and B in 3 space are parallel if and only if A cross B is equal to 0, the 0 vector. Now that's different to the 0 scalar, which is a number. So the 0 vector is a vector with components 0. So let's see that this works. So let's suppose we have a vector A in 3 space, so it's A1, A2, A3, and B is B1, B2, B3. Now let's just calculate the cross product of any vector that is parallel to A. So what I want to do is specialize this to saying, what if B is equal to a multiple of K? So that B is equal to K times A1, K times A2, and K times A3. I can see this is a typo, so let's note it down. So B equals KA1, KA2, and KA3. And so what we're doing is we're calculating the determinant of A with this B. So I'm going to do that here. A1, A2, A3, and then I'll put in KA1, KA2, KA3. And since I'm going to calculate, I need to clear the letter A out of my calculator's memory here. Okay, because I want to treat that as a symbol. All right, so let's have a look here. So it seems like the typo doesn't extend to what follows. It's only in this third coordinate of B there. All right, so remember, if you're calculating the determinant of this matrix here, then we have I times the 2 by 2 determinant obtained by crossing out the row and the column that I is in, right, and forming that determinant there. Likewise, we move on to the second element in the top row. So J, we cross out the row and the column that J is in, and the matrix that remains is A1, A3, KA1, KA3, but we put a minus sign in front of that determinant. These are going to alternate. Okay, and then finally, to calculate the last 2 by 2 determinant, to work out the third component of the cross product, we cross out the row and the column that the K is in, and we're looking at A1, A2, KA1, and KA2, and calculating that 2 by 2 determinant. So that's going to give us A2KA3 minus KA2A3, and you can see that that's going to give 0 there. Likewise, this gives 0 and this gives 0. So if I calculate this determinant, the computer tells me that it's 0, but it's symbolically performed. The I, J, and K here, I have to then go and replace with the vectors. So I should read this output here as the 0 vector. All right, so we get the 0 vector out of that calculation. Now, conversely, because remember, when you have if and only if in a statement, it says, the way to read that is, if A and B are parallel, then A cross B is 0, and if A cross B is 0, then A and B are parallel. So that's how you would read an if and only if statement. So let's go and do the converse now. Conversely, suppose that A cross B is the 0 vector. To show that A and B are parallel, we have, assuming here that B is equal to B1, B2, B3, so we calculate this determinant, we get this symbolically. Now we assume that it's the 0 vector, and so that gives us 3 scalar equations. All right, now you've got to make a few assumptions in which you don't lose any generality. So if A3 is 0, then these systems of equations simplify quite a lot. We get A2, B3 is 0, A1, B3 is 0, and A1, B2 minus A2, B1 is 0. So in this case, you have to have B3 equals 0, since A1 and A2 cannot both be 0, because otherwise we would have A is the 0 vector. Right? So we're assuming here that A is not the 0 vector. Alright, so if A3 and A2 are both 0, then A1, B2 is 0, so that B2 is 0, and it follows that A and B are parallel. Okay, so if A3 is 0, but A2 is not 0, then B1 is B2 over A2 times A1, and B2 is B2 over A2 times A2, so that by letting K be equal to B2 over A2, we get that B is equal to K times A. So this section of the proof is a little bit more complicated, all right? And now finally, if A3 is non-zero, then the 3 equations give us that B is equal to B3 on A3 times A1, B3 on A3 times A2, and B3 on A3 times A3. And so if we let that constant K be B3 on A3, we actually have B is equal to K times A. All right, so probably would involve some careful writing of this stuff by hand to fully understand how that works, right? And so if you don't want to, no big deal. You can just believe the claim here. All right, moving on. Scalar triple product. So a parallelepiped, now try saying that 3 times, is a 3-dimensional figure in which each of the 6 sides has opposite sides that are parallelograms. See figure 8. Okay, let's have a look at figure 8. So here is an example of a parallelogram, but we make it out of 3 vectors. So you can see that this outer face here is parallel to the back face. The top face is parallel to the bottom face. This side is parallel to this side. And each of the 6 sides of this parallelepiped are parallelograms themselves. Okay, so that's basically the definition of a parallelepiped. And you can see here in bold we have vectors that we're using to describe the parallelepiped. Alright, so we can calculate the volume of this figure using what's called the scalar triple product, where this single bar on the outside is the absolute value. So I'm going to have to swap notations when we calculate a few things. I'll swap this for the words ABS, because we also use this for the determinant sometimes, right? So mathematics occasionally reuses notation. Alright, so to disambiguate this, I'm going to call this absolute value just ABS instead of the 2 lines here. The volume of a parallelepiped with sides made from the vectors u, v, and w can be calculated by taking the absolute value of the determinant of the matrix whose rows consist of the vectors u, v, and w. Okay, so in other words, what you do is you just calculate the absolute value of the determinant. Now here's why we have the words ABS rather than absolute value, because we're also using the vertical bars for determinant there. So we calculate this via the absolute value of the determinant made from just putting the 3 vectors in a 3x3 matrix. So you put the coordinates in the top row, then the coordinates of v in the second row, and the coordinates of w in the third row. You calculate that determinant and then take its absolute value. So that's, I would think, is the easiest way to calculate the volume of a parallelepiped. Alright, but let's go over why this is true. Now up here it's given as the absolute value of u dot v cross w, but I'm going to show you that that's the same as this. Alright, so absolute value of u dot v cross w is the absolute value of u dot the cross product here, which remember is a determinant. So we calculate that determinant, we get this, it looks a little bit messy, and then we dot that with u, and so we've got to multiply u1 times this, u2 times this, u3 times this, and then add the result. Alright, and take the absolute value. So you'll note that it's the same as when you take the absolute value of this determinant. And so I'll just show you that the computer gives that same result. So I'll just get rid of everything before I start typing. Okay, so we have u subscript 1, u subscript 2, u subscript 3. Now I'm going to copy and paste this into the second row and change the u to a v. And I can see that the v is in memory, so I'm going to clear that. Okay, and then we'll do the same thing here. Change that to a w. and let's calculate the determinant. Okay, so this is what we get. And then we wanted to take the absolute value of that, right? So I would take the absolute value of this. All right, now in another way, you calculate it like this, but you can see that you get the same result here, right? So I hope that convinces you that this is the same as this, and so you can calculate the volume of a parallelepiped perhaps a little easier using this formula, right? Because you don't have to muck around with a determinant and then a dot product. Okay, so let's have a look at example 5.3, where we have 3 vectors, and we want to calculate the volume of the parallelepiped with sides given by the vectors u, v, and w. Now it's shown in figure 8, so let's have another look. Figure 8 was probably this way, wasn't it? Yes, figure 8's here. Okay, so what we're doing is we're just using this fancy formula where we take the coordinates of u, v, and w, we put them into a 3x3 matrix, we calculate the determinant of that matrix, and then take the absolute value. So we have 1 times the determinant of the 2x2 matrix, minus 1, minus 1, 1, 0, and then minus, remember the second part has a minus in it, minus this number 3 times the 2x2 determinant obtained by crossing out the row and the column that the 3 is in. So minus 1, 2, 0. Okay, and then plus this 2 times the 2x2 determinant obtained by crossing out the row and the column that the 2 is in. All right, so we have this. And so 1 times, in brackets, 0 minus minus 1. And then minus 3 in brackets, 0 minus 2 times minus 1, and then plus 2 in brackets, minus 1 minus minus 2. So we have the absolute value of 1 minus 6 plus 2, which is the absolute value of minus 3, and the absolute value of minus 3 is plus 3. So the volume of this parallelepiped is 3. All right, so that calculation was not too bad. I mean, it could have potentially been somewhat worse if you would have calculated it using this method, right? I mean, calculating the dot and the cross product there. All right, let's continue on. So projection vectors, what are these? So I'm going to display some vectors in blue and red, or red and blue. So recall that a unit vector is a vector of norm 1. To create a unit vector, now we display that we're talking about a unit vector by putting a little hat on the top. See that little hat on the top of that V? So to create a unit vector v hat in the direction of the non-zero vector v, we must divide by the norm of v. So in other words, v hat is 1 over the norm of v times v. And that gives a unit vector that has the direction of v and norm 1. And so you could just take the norm of this and you'll find that the norm of this new vector is equal to 1. Okay, question or example 5.4. What is the unit vector in the direction of the vector 2, 2, 1? So we need to calculate the norm of it. So the norm of 2, 2, 1 is the square root of 2 squared plus 2 squared plus 1 squared, which is the square root of 4 plus 1, or the square root of 9. The square root of 9 is 3. So we have 1/3 times the vector p. The vector p is 2, 2, 1. So our unit vector is 1/3 of 2, 2, 1. Now it's a matter of taste as to whether you bring the 1/3 in or you leave it out. Okay, so it's easy to check that the norm of 2/3, 2/3, 1/3 is equal to 1. All right, so now we're going to look at a new concept called the projection vector, or the projection of v1 onto v2. Let's have a careful look at this diagram here. So what we're doing is we have a vector v2, a v1, we have a vector v2, and what we're doing is we're sort of, you could imagine this by shining a torch onto the vector v1 in a direction perpendicular to v2 so that its shadow onto v2 gives you one component of the vector v1 in terms of v2 and a vector perpendicular to v2, right? So that also kind of explains the use of it. All right, so the projection of v1 onto v2 is given by this projection formula. Now, when I write this, I put the v2, what it's projected onto, as a subscript, and bigger, like a function, I put v1, right? So the bigger one appears to be shining onto the smaller one, innate to memory of what we're talking about here. All right, so this is given by the dot product of v1 and v2 over the norm of v2 squared times v2. Right, now the first part of this, the fraction part here, that's a scalar and v2 is a vector. So we obtain a vector here. So you can see that it has to be parallel to v2 just in its description. So it's calculated so that it will be a unit vector though. All right, so to see that this holds, let v1 equal a plus b, where a is the projection of v1 onto v2, and b is perpendicular to a, right? So that a and b add up to v, and what we're interested in here is the projection. Let theta be the angle between a and v1. Then cos of theta is the norm of a over the norm of v1. Okay, so rearranging this, the norm of a is v1 cos theta. Remember, a is the projection that we're after. So multiplying by the norm of v2 gives us the norm of a times the norm of v2 equal to the norm of v1 times the norm of v2 cos theta. Theta is the angle between them. But remember, the dot product formula for the angle between two vectors says that this is v1 dot v2. So we worked out that the norm of a2 by rearranging this formula here, dividing both sides by the norm of v2, we have that the norm of a is equal to v1 dot v2 over the norm of v2. Now a has the same direction as v2, so we must have a equal to the norm of a times v2 hat. That should say v2 hat there. All right, but v2 hat is 1 over the norm of v2 times v2, so we just sub that in there. And then we move the denominator together, and so that we have over the norm of v2 squared. So we get that a, which was the projection of v1 onto v2, is v1 dot v2 over the norm of v2 squared all times v2. Okay, and so that's our projection formula, and this is the derivation of the projection formula. Now, I think up next we have example 5.5. Okay, so we have two vectors. A is 2, 1, 0. B is -1, 1, 3. All right? So I've got these also on the right-hand side. A is 2, 1, 0, and I'm displaying that in red. B is -1, 1, 3. I'm displaying that in blue. And I want to calculate the projection of B, the blue one, onto A. All right, now let's move this around, C. Now you see that A does not have a K component there. So that's why it's on the bottom of the box, right? So the box is the XY plane. All right, but remember you can move it around. So I've just displayed arrows, right? You can move the arrows around and you have the same vectors. All right, so we're calculating the projection of B onto A. Now, geometrically, what this means is it's the direction of the shadow, or so you sort of have a shadow, a light pointing um, in a direction perpendicular to A, down onto A, and we're interested in what that shadow looks like, right? And the use is in finding components of the vector B in the direction of A, right? So we can represent the vector B in terms of A. All right, so the projection, it's calculated right here using that projection formula. So we take the dot product of the two vectors. A dot B is 2 times minus 1 plus 1 times 1 plus 0 times 3. So we get minus 2 plus 1 plus 0 for the dot product of A and B, which simplifies as minus 1. Now, the norm of A is the square root of 2 squared plus 1 squared plus 0 squared, so the square root of 5. But remember, then we square that norm, so we have minus 1 on 5 times the vector A, which was 2, 1, 0. So this gives us that our projection of the vector B, that should say B onto A, is minus 2/5, comma, minus 1/5, comma, 0. And we could also write that as minus 2/5 I, minus 1/5 J. All right, but I'm going to show you this projection here. So when you project B onto A, you have, you see it has a direction in the opposite direction of the vector A. It is parallel to A, but it carries some of the direction here of B, right? It's shining a light onto A, casting a shadow of B, onto A. So that's what you're seeing here, right? So if I rotate this around, it's perhaps clearer that that's what it is, you see? Let's have a look from pointing down from the blue arrow. All right, so it's just like this. It's the shadow of blue onto A. All right, so if I put another vector perpendicular to A, I can show how a green vector and, say, another vector would add up to blue, so that I can resolve the blue vector in terms of the red vector A, right? And that can be very useful, especially in little problems on like Newtonian physics, where you have, say, a block sitting on an inclined plane, and you're trying to determine whether the block will slide down the plane, right? It's helpful to be able to express another vector in terms of a vector that's not necessarily parallel to each of the axes. All right, so this is just a tool for calculating vectors in some applied problems. And that brings us up to the next chapter, so I'll see you for that one later.